Welcome dear students to this new video on CPU scheduling. In this video we'll be discussing about round robin scheduling. Now as far as round robin scheduling is concerned, basically uh, in this scheduling we are having a time quantum or a time slice. It is basically a short span of time and every process basically execute for that slice. That is, suppose there are 5 processes in the system, so each process will get CPU's execution time in certain milliseconds, and that milliseconds depends upon what time quantum or slice we are using. So each process gets a small unit of CPU time. So during that small unit of CPU time, that process executes partially, and in case during this execution phase that process is not complete, it comes back into the ready queue and then again waits for its turn, so that when it turn comes again, so it will again get the CPU's access for that time quantum. And in this way there might be a case that that process might have to come repetitively for CPU's execution, and once its entire CPU burst time has elapsed, then that process will terminate. Fine. Now as far as this round robin scheduling is concerned, it is preemptive in nature. It is preemptive in nature because every process which comes for execution with the CPU will only execute for that time slice what has been set, and after that time slice has elapsed, that process will again append itself at the end of the ready queue and will wait over there for its turn again. So as far as this round robin is concerned, basically, so let's assume that if there are n processes which are waiting in the ready queue and the time quantum set is q, so then each process gets 1 by n of the CPU time in chunks of at most q time units at once. So what I'm saying over here is, suppose we are having a time quantum of q time units, fine, and there are n processes in the system. So each process will have to wait at most this much time units, n minus 1 into q. For example, let's suppose we are having 5 processes and the time quantum set is 2. Fine. So if we put both these values over here, the number of processes are 5, the time quantum is set to 2, so that means 5 minus 1 comes out to be 4 into 2, that is 8 time units. That means after every 8 time units each process will get its turn. At the most, the waiting of that process in the ready queue will be 8 time units. That's it. So as far as, again, one more point over here is, every process is going to get itself executed after a certain span of time. There is no unlimited waiting over here. Secondly, now there are few issues also over here, and one of the issue is that we have to set the time quantum keeping into consideration certain aspects, because if the time quantum is set to too large, in that case this round robin scheduling will behave just like FIFO, that is first in first out scheduling algorithm. For example, let's suppose the time quantum set is, if I let's assume only the time quantum set is 25 milliseconds, and we are having the processes which are in the system. Let's say one of them is 8, needing only 8 milliseconds, second one is requiring 12 milliseconds, third one is requiring, let's suppose, 9 milliseconds, fourth one is requiring 4 milliseconds, fifth one is requiring 2 milliseconds. Now because time quantum set is set to the value that is 25, but all the processes are having the burst time quite less as compared to the time quantum set, so in that case whichever process gets the excess of CPU will complete itself in that span of time, because at one go every process will be getting this much amount of time. But Actually, they need very less than that. So the behavior will just like be the one who gets the access will complete first, then the second one will complete, then third one will complete, then fourth one will complete, and so on. So its behavior will be just like first in first out scheduling algorithm. Now, second thing is, if we set this time quantum too small, let's suppose I'm taking it as smallest value, suppose of 1 milliseconds. In that case, that smaller time quantum will result in large number of context switches. And we know that if the context switches are large, our system will be not be will be optimally used, because context switch itself is an overhead, and if the number of context switches are high, so the overhead will be also too high. So we need to keep this thing in mind that whatever time quantum is to be set, it should not be too large or it should not be too small, because both of these are not going to give us some fruitful results. So fine. Now let's have a look at some scenario where we'll be applying round robin scheduling algorithm and see how actually the system works. So let's see that. Now suppose that we are having these set of values with us. First of all, if you observe over here, we have set the time quantum to 2 milliseconds. Now we are having 5 processes with different arrival times given over here, and also the burst times are mentioned, and we are supposed to calculate the average waiting time as well as the average turnaround time. So we know that the very first thing before we begin with the calculation of these two things, we need to prepare a Gantt chart based upon which we'll be calculating the completion time. So let's prepare a Gantt chart for this. So there is something which we should be very careful while we are selecting the next process for execution. So I've taken first of all, I'll be going for preparing a Gantt chart, but also I'll be maintaining a ready queue over here so that to avoid the confusion regarding who will come next. So if you see over here, at time t0 only process which was waiting in the queue was p1 because it came at time t0. At that time, no other process was over there. The slice is set to 2, which means that every process will be given 2 milliseconds in one go. So at a time 2 milliseconds for each process. So P1 comes over here, it executes for 2 milliseconds. That is from 0 till 2. But actually it needed 5 milliseconds. So by the time 2 seconds have elapsed, already P2 and P3 had entered the ready queue. So earlier only P1 was there, but after 2 seconds, P2 was also over there, then P3 was also over there. Fine. Now, has P1 completed? No. It only got 2 milliseconds out of 5 milliseconds. It needs 3 more milliseconds, but it has to wait for that. So this P1 is preempted. Now question arises, where will this P1 go? This P1 will move into the ready queue. So which are the processes which are there, which are at present in the ready queue? They are in this sequence. P1 was shifted to CPU for execution, and P2, P3 were there. Now P1 is preempted. So P1 enters in the ready queue and is waiting for its next turn. So which is the next process in the queue? It is P2. So now we are fetching this P2. So once we are fetching this P2, so P2 got the access of CPU. It executes there for again 2 milliseconds. So from 2 to 4, it is P2 which is executing, but its requirement was of 3 milliseconds. It executed there only for 2 milliseconds. So that means it needs one more millisecond so that it can complete its execution. So now as of now 4 seconds have elapsed, 4 milliseconds have elapsed. So by the time 4 milliseconds have elapsed, process P4 as well as P5, they have also arrived in the ready queue. So P4 and P5 has also arrived in the ready queue. But has this P2 completed? No. So by 4 milliseconds have elapsed. So the queue which is as of now in the processes which are waiting in the ready queue are in this order, and P2 has not yet completed because 1 millisecond is more required. So this P2 is preempted and P2 comes in the ready queue in this very way. So now after P2, who was the next process which was waiting? It was P3. So now P3 will enter and get the access of the CPU. So P3 executes over there, though the time quantum set is for 2 milliseconds, but P3 needs only 1 millisecond. So P3 will execute for 1 millisecond only, and then again CPU will be idle. I mean to say CPU will get the next process in the queue. I have taken it 0 because this process has completely, P3 has completely executed. That is why I have set this value as 0. So because P3 has completed, so P3 now need not to move on to the ready queue. Why so? Because P3 has terminated. Now, which process is in the ready queue or who will get the turn now? So if you see over here, it is P1. P1 is in the ready queue who will be getting the access of CPU this time. So we are giving access to P1 over here, and P1 is getting access for 2 seconds, 2 milliseconds. That means from 5 till 7, the control of CPU is with P1. But P1 needed it for 3 milliseconds, got for 2 as of now. So that means it needs 1 millisecond again. So this means what? Again P1 is preempted and is shifted from the CPU's running state onto the ready queue. So P1 will again come back in the ready queue after P2. So next, who is the next process which is waiting in the ready queue? It is P4. So we are fetching P4. So P4 gets access of CPU for 2 milliseconds. So P4 executes from 7 till 9, and actually P4 needed only 2 milliseconds. That means in a single go, this process has executed. Fine. So now who is the next process in the waiting queue? After P4, it is P5. So P5 is fetched from here and is shifted from this place onto the running state. So P5 is executing. P5 needs CPU for what span of time? It needs it for 3 milliseconds, but is getting the quantum of 2 milliseconds only. So that is why again it will be preempted from here. So it is preempted means it will append at the end of the ready queue. So P5 will append at this place. Now comes the next process is P2. So P2 will enter into the running state. So we are putting P2 over here. Fine. And P2 needs only 1 milliseconds this time. So that is also no more, that is also, P2 is also completing its job. So from 11 to 12, it is P2 which is executing and is now terminating. That means no, it will no more come into the ready queue. Then who is after P2? It is P1. So P1 comes over here now. P1 needs CPU for what time? It needs CPU for 1 millisecond. So we are giving it to P1. So P1 executes there for 1 millisecond. That is from 12 to 13. The control is with P1. So this time P1 also finishes. So P1 terminates. Then who is waiting now? It is P5 now. So it is P5. So P5 will get the access of the CPU. That is P5 enters from ready state onto running state. So P5 needs CPU for 1 millisecond. So that means from 13 to 14, it is P5 which is executing. Now this is the Gantt chart which we have got for the scenario given in this system. So now let's see the completion times of these processes. So if we see the completion time of P1, so P1 completes at what span of time? So let's look the entire Gantt chart and see for the last entry of P1. So P1 completed at 13 milliseconds. So I'll put 13 as the completion time for P1. Then let's see P2. P2 completes at 12 milliseconds. So P2. P3 completes at 5 milliseconds. So 5 is the completion time of P3. Then for P4, the completion time is 4 milliseconds. And for P5, the completion time is 14 milliseconds. So then let's calculate the average turnaround time. Sorry, the turnaround time for individual processes so that we can calculate the averages of that after this. So it is completion time minus arrival time. So 13 minus 0 is 13. 12 minus 1 is 11. So in this case it is 13. Now next thing is we have to calculate the turnaround time for P3, that is 5 minus 2, this comes out to be 3. Then 4 minus 3, this comes out to be 1. And at last we are having 14 minus 4, so this comes out to be 10. So if you observe over here, let me see whether I've done the entire things correct. Sorry, I made one mistake. I believe the completion time of P4 was 9 milliseconds, so it should be 9 over here. Accordingly, 9 over here, and then 9 minus 3 comes out to be 6. So kindly make this correction. Actually, this is 9. Completion time of P4 is 9 milliseconds. Now, the next thing is we have to calculate the waiting time for every process, each of these processes. So 13 is turnaround time minus burst time. Burst time is 5, that is 8. Then 11 minus 3 is again 8. Then turnaround time for this is 3. Burst time is 1, so this comes out to be 2. Then 6 minus burst time is 2, this comes out to be 4. Then 10 minus 3, 7. So let's add all these values to fetch the average turnaround time. So average turnaround time is, it is 13 plus 11 24 plus 3 27 plus 6 27 plus 6 33 plus 10 43. So 43, and we have to divide by total number of processes over here. So we are having total of 5 processes. So this comes out to be 5 8s of 48.6 millisecond is the average turnaround time for this system. And if we calculate the average waiting time, again add the individual waiting time of all the processes, that is 8 plus 8 16 plus 2 18 plus 4 22 plus 7 29. So 29 divided by, we are supposed to get divided by 5, as 5 is total number of processes in the system, so it comes out to 5.8 milliseconds. So this is how the round robin scheduling works. The only thing is, when we are evaluating such a system, we need to prepare a ready queue of the processes, because whichever process is preempted, it should enter at the end of the ready queue. So we need to maintain this queue, otherwise sometimes problem might be over there. So we have maintained this queue efficiently, that is why there was no issue in evaluating this system. So now let's move on to the pros and cons of round robin scheduling. Now, as far as the pros of the advantages of round robin scheduling is concerned, the first thing is its fairness. That is, every process gets equal amount of CPU's time for execution, and this means what, each process will get its turn. No process will be starving for accessing the CPU. So that is the positive part of RR scheduling, or round robin scheduling algorithm. Secondly, it is very ideal for time shared systems. So as the name says itself, each process is basically getting time to execute with the CPU. So it is very ideal for time shared systems. Obviously it is simple and easy to implement, but we need to prepare a circular queue for this to manage the processes. So if you see over there, we have maintained a ready queue, a circular kind of ready queue. Whichever process is executing, until and unless it is not complete, that means it doesn't terminate, it comes back into the ready queue at the end, and it continues in this process. It moves into the cycle uh, for its entire phase till the time it basically terminates. Now there are few issues with regard to round robin scheduling. The main issue is, obviously we have observed that because each process is getting a limited time quantum, so that process might have to go for multiple times into ready queue. That means a large number of context switching is over there, because and we know that this context switching is an overhead. So this round robin scheduling involves frequent context switches. That is why in the beginning I shared with you that if the time quantum is very small, in that case the context switching will be on the larger scale, resulting in large overheads. Second thing is, the issue over here is the selection of the quantum. So it itself is a challenge to basically setting the optimal quantum for some system. It is quite difficult. So we have observed that if it is too small, in that case the context switching is on the larger side, and if it is too large, then the behavior of the system would be just like a first come first serve algorithm. And this means what, some processes might have to wait for larger periods of time. And we have seen that if FCFS is over there, it might also lead to a convoy effect. So one more disadvantage of the system is that basically this scenario is not suitable for every kind of tasks, because there are few tasks which needs priority, which needs to be done on priority basis. But here there is no priority, high priority process. Even if it is high priority process, it has to wait for its turn and will only get the access of CPU for that limited period of time in one cycle. So that might create a problem, because if the process is high priority, it has to follow the same protocol which is set by round robin scheduling. So I hope that you have got an idea how round robin scheduling works. So in the next video, we'll be discussing about priority scheduling. Thank you.